It's my pleasure to announce today's speaker, who is Jeff Scargle from NASA Ames. Jeff's in the Planetary Systems branch in the Space Science and Astrobiology division, and he's going to talk to us today about tools for probing the universe, from the smallest to the largest and all scales in between. Jeff is a research astrophysicist, and he studies high-energy astrophysics, especially processes with emissions in X-ray and gamma rays. And he's pioneered a lot of techniques for essentially automating data analysis and processing. Jeff got his BA from Pomona and his PhD in astronomy from Caltech. And it's our pleasure to welcome him today to SETI.
Well, thanks very much. And let me start off by saying I'd like to keep this informal and interactive as much as possible. I guess the usual policy is to ask you to save questions to the end, but I'm going to encourage questions as we go along, especially about details. And I'll try to repeat the question because I know the issue is that it's hard to hear for the taped session. And it's really an honor. I really appreciate, especially if you look at the list of upcoming and past speakers, it's really an honor for me to be in this session. And this talk is going to be, may seem like a bit of a montage at some points because there are sort of apparently distinct topics, but I think at the end you'll see that kind of they all fit together, with the possible exception of something in the middle. Here's a kind of an outline of what I'm going to talk about. I'm going to start by defining what I mean by a data space and how that connects to what I probably should put in quotes as a real space, and then talk a little bit about the scales in the universe, the largest and smallest. And then I'm going to talk about I see there is a flaw. That there should be a space between Voronoi and tessellation. Those are two separate words. I'm going to talk about a data segmentation approach that may seem mathematical and abstract, but when I show you specific examples of applying it to real data in astronomy, I think you'll see what it's all about. Kind of in the middle, there's what I call a statistical interlude, which is really not directly connected to these topics, but is kind of gives me a chance to vent about how statistics is being misused even by otherwise intelligent people, even today. Okay, and the kind of underlying fundamental notion is that of a data space, and here's an example of the connection between real space and a data space. This is the Fermi Gamma Ray Telescope, which I'm associated with as an affiliated scientist, and it was launched last year and is now in space, churning out lots of really great data. Although I just got an email this morning saying there was a glitch and it actually was shut down, at least partially, for a while, and that's a very rare thing. That only happened once before. But the real space is, of course, the universe. Here's just a galaxy that doesn't really matter too much what it is. I'm just trying to symbolize the astronomical universe, the real physical entity, the space that we're trying to study. This is a picture of the instrument, the Gamma Ray Telescope, in the lab at SLAC before it was launched. And here's a sort of a cartoon of how it works. Gamma rays come in and cause pair conversion, and the electrons generated in the conversion process are tracked, and one deduces the direction that the gamma ray came in to the telescope, and then in terms of the data representation, one can plot a point for each gamma ray photon in terms of its position on the sky. And here's a map of a small part of the sky, declination and right ascension, and showing, in fact, this is not actual data. This was simulated data before the the launch. But so what I'm going to concentrate on is this concept of a data space. A space, in here it's two-dimensional, but in astronomy we now have data spaces of higher dimensions. In particular, redshift surveys allow one to position individual galaxies in a three-dimensional space because we can measure the redshift and therefore the distance. So think of this as just one example of a data space that happens to be two-dimensional. And the data are not measurements as such, they're locations of points. So this is one example of a data mode where the data is conveyed by the position of an individual photon in this case. Or in the three-dimensional redshift surveys, the point is a galaxy and the data is conveyed by its position in that three-dimensional space. Okay, now I'm going to introduce the scales of the universe, and I think everybody knows the Hubble constant and its history. I found this on the web somewhere, and I thought it was really interesting. It's a plot of this so-called Hubble constant as a function of time. This is not the actual value of the constant, it's our measurements of it. And an interesting point is that Hubble's original value was 500, completely off scale. So starting from the early days until now, there's been quite a change. And nowadays, we have a much, well, is this better defined? There's still a lot of scatter, but there's now a fairly canonical value of 71 kilometers per second per megaparsec for the. Oh, sorry. It's a measure of the scale of the universe in a way. It's a constant that arises in models of how space expanded from the Big Bang. And in fact, you'll see in a minute how it relates to the size of the universe, the radius of the universe. In fact, here is exactly that. Here, the canonical, the so-called concordance cosmology. Cosmology is turned into an exact science in the last 10 years or so, and it's somewhat euphemistically, I think, called concordance cosmology, because not everybody agrees with the numbers. But anyway, the value of the Hubble constant has kind of settled down at that value, and that converts to a size for the universe. Well, what do I mean by that? The universe is open and open-ended in a way, but this is essentially the distance from the Earth to the so-called horizon, in the sense that if there is universe beyond that radius, we can't see it. Photons have not had enough time to reach us from that distance. So it's kind of like a cheat. It's not the actual size of the universe, but it's the largest size that we can observe. So it's sometimes called the radius of the observable universe in various units, parsecs, centimeters, and this incredibly large number, Planck lengths, which I'll define in a minute. But that's the point I'm trying to make, is that this is the large scale, and there's a small scale. There's the smallest possible scale at which measurements can be made. And if there's one thing that I hope you'll get out of this talk, it's what this means and how kind of incredible and somewhat anti-intuitive this is. We tend to think of space and time as continuous, and we can measure smaller and smaller distances, and there's no limit to that we could, in principle, measure any value for a separation between 2 points in space-time. But in fact, that is not true, and a simple way to see that is what's called the sort of a generalized uncertainty principle. And the smallest spatial interval that can be measured is this so-called Planck scale. And it's this number, 10 to the minus 35 meters. And physically, it's this combination of fundamental constants. H is the Planck constant from quantum mechanics. C is the speed of light from special relativity. And G is the Newton's gravitational constant. And one way of thinking of this Planck scale is that it's just dimensional analysis. If you put together this combination of numbers of fundamental constants, you get something that has the dimensions of distance, and it ties together the large and the small. And so the argument is, if you're trying to unify gravity and quantum mechanics, the so-called grand unified idea of unifying everything, this must be a constant that's relevant, because it ties together all of the fundamental physics theories at the smallest scale and at the largest scale. But there's another more meaningful approach to the so-called Planck scale, and that's this uncertainty principle. You're probably familiar with the Heisenberg uncertainty principle, which says that if you fix the energy of something, it's the time at which you fix that energy is limited in accuracy, or if you fix the position of an object, its momentum is uncertain. And that mathematically, in this equation, the uncertainty in the measured length is the ordinary uncertainty principle, but there's another source of uncertainty, namely the photons that you use to measure an object's position not only can give a kick, a momentum to the thing you're trying to measure and cause its position to be uncertain, but in addition, its gravitational field gives a perturbation to the thing you're trying to measure. So instead of just the ordinary uncertainty principle kick from the photons having momentum, if you consider the perturbation due to the gravitational field, even if a photon with zero mass has a gravitational field, because energy generates gravitational field. So anyway, and just including that effect and putting formulas in for the known gravitational influence of a photon, you get this extended version of the uncertainty principle. And if you minimize this uncertainty, you find that this magic constant arises. So if you don't understand the details, or I really haven't had time to explain how you get from this expression to this minimum, but the notion is that there is a smallest scale of space, and there's also a smallest time that can be measured, and a smallest mass, and a largest energy. Because the energy is the reason why energy is large, if you think about it, just has to do with how energy is used to measure things.
Smallest mass seems awfully large, though.
The comment was the smallest mass. Yes, it compared to these other numbers, this mass seems relatively large. I don't know what to say. It's that's the way it turns out. It's
Is it -8?
Yes, -8 kilograms. Unless there's a typo. I don't use that number very often, so I may have an error in there. But so anyway, that's a good question. And I know exactly what you're saying. The scale of mass seems relatively large compared to the smallness of time and length. But in this talk, I'm only going to be concerned with length. And if you want more details, here's a reference to a paper by Ron Adler, who's at Stanford, and Santiago, who go into the details of how you derive this.
It does seem weird, because that would imply that every elementary particle has a number. But you can't measure the mass
Yeah.
of any
Yeah.
elementary particle.
The comment was that seems, again, this mass seems too large because it's large compared to masses of elementary particles. I'm not sure quite how to answer that. I think my statement that this is not the smallest mass that can be measured. It's a characteristic scale for mass. And by the same token, this energy is obviously not the smallest energy that can be measured. It's a scale of energy that corresponds to this uncertainty principle. Anyway, good good questions, and I don't know what the answer is. Okay, and this is just a kind of drawing those two numbers that we got before. The largest scale, that is the size of the visible universe on a log scale, is this number roughly 10 to the 26 meters. The Planck scale is 10 to the minus 35 meters. And you see it's really small compared to even the size of electrons and quarks. So this is kind of a no man's land. This is completely unexplored. And in some sense, you could think we'll never be able to measure anything down at this scale, that our measuring equipment and devices kind of limit us to above this scale. One of the exciting things about astrophysics in the last few years is that there are now astrophysical techniques which may give a possibility of measuring things down to this scale, and I'll talk about that a little bit at the end. Because one of them happens to be by using the Fermi gamma ray telescope. Okay, so now jumping to an algorithm that's called Bayesian blocks. It's a way of dealing with data over any scale, and starting with a data space. And here's an example. The data space I'm talking about here is time. These four plots are histograms of photons coming from a gamma ray burst. In other words, the vertical axis is the intensity of the gamma ray source, a so-called gamma ray burst, and the horizontal axis is time. And this is one of the longer gamma ray bursts that extend over hundreds of seconds of time. And these are four energy channels. And this is a typical plot that you see in astronomy and physics and science in general, namely a histogram of a bunch of events. Each of these bins in time is the sum of the number of photons that were detected over that bin. Well, one of the criticisms that people have of this, and I pursued, was that the structure you see here is determined by a pre-chosen bin size. You have to decide how big to make the bins. And do you make them big enough so you get good statistics in each bin, or do you make them small because you want to get good time resolution of a sharply defined structure? So it's really a poor way to represent the data, even though it's a common way. What you might like to do is something more like this. This is another way of doing histograms, where you, instead of fixing the bin size, you say, I want every bin to have the same number of events in it, so that when the source is bright and changing, I have more bins. You can't see it too well, but there are a lot more bins. They're smaller in time to get better resolution where you have more data. It's kind of an adaptive binning. And the Bayesian blocks algorithm in this one-dimensional case is an extension of that idea, where you say, I want the bins to kind of adjust to the data and not be fixed and determined by the data. And the mathematical definition is that this is in each case, in each of these four energy channels, this is the best representation of the data in terms of in terms of intervals over which the intensity is constant. In other words, over this interval, there are fluctuations, but those are all just statistical fluctuations due to the fact that I'm counting a finite number of photons. And so the algorithm finds the best possible partition of this one-dimensional data space into intervals over which the signal is constant. And here's a two-dimensional example of the same thing. Here's, again, one of a map of photons on the sky. In fact, it's the same map that I showed earlier in terms of the Fermi telescope. This is a patch of the sky, and each point represents a photon. Well, how are we going to partition this two-dimensional space? It seems like it's much more complicated than in the one-dimensional case. Well, that's what the Voronoi tessellation is. It's a partitioning of the data space into cells, where each cell corresponds to a single data point. And the definition of these cells is that they represent all of the data space that's closer to the the data point that you're talking about than to any other data point. So it kind of represents the sphere of influence, in a way, of each data point. And where the points are more dense, the cells get smaller. So in a way, this is a nice way to represent the density of the underlying signal, because the density is roughly proportional to 1 over the cell area. And there's a lot of mathematical details, and this algorithm to define these cells turns out to be really useful in computer graphics. So there are a lot of really fast algorithms that computer people, I want refrain from calling them geeks, but computer people have spent a lot of time making this algorithm really fast. And in fact, there are algorithms that can do this kind of a partitioning of higher dimensional data spaces in very short time. Okay, the next step is to notice that there's another useful feature of these Voronoi cells, namely, if you draw a line or an arrow from the centroid of the cell to the data point, because in fact, depending on the neighboring cells and data points, the actual data point itself isn't necessarily near the center. If there's a gradient of density, I think you can intuitively see that the point may be very close to neighbors in one direction and far away from neighbors in another direction. So in the final analysis, what that means is that this little line represents the gradient of density, in the sense that its direction is in the direction of increasing density, and its magnitude is roughly proportional to the density gradient. And in a few more slides, I'll blow up this rectangle so you can see it a little better. It's almost like little amoebas or something are pointing toward the peaks of density. And here's an even more expanded version. So this geometric construction of finding the Voronoi cells for each data point gives you not only an estimate of the density of points, but it gives you an estimate of the gradient of density. So you can find where this represents a gamma ray source, where the photons are much more dense in the center of the source than they are on the edges. And so you can identify point sources in gamma ray data very, very quickly this way. And if you take away all the other cell edges, this is kind of a nice representation of the density and the gradients. And so from this, you can construct a kind of the structure of sources by combining cells together. And I think I'll skip this for the most part, because it's kind of hard to see. This is meant to be a three-dimensional plot where what you see are these cells kind of raised up depending on the density. In other words, the smaller the cell is, the higher it's plotted in this plot. So this is a point source, and near the center, the Voronoi cells are really small, so they're plotted very high. So this is like a discrete version of a three-dimensional surface plot, which you often see in computer displays. Okay, here's a statistical interlude, and maybe some of you were in the abstract. I mentioned some things having to do with medical and pseudoscience, and here's where I talk about that a little bit. You probably know that in medical studies that are clinical, where like a drug test is carried out, they're very expensive to do, and so typically they're usually small studies. And over the decades, there's a whole topic called meta-analysis. In fact, I heard this mentioned on one of the TV news programs this morning about a cancer study. And the idea here is that you try to increase the statistical significance of these studies by combining them together, by taking these summaries the statistical summaries, like the mean and the variance or whatever of the published studies. And without reanalyzing the original data, you just lump them together and construct a overall estimate of the significance of the result with the drug or whatever it is. And people realized that there's a potential problem with this meta-analysis or collecting together of individual studies, in that if there's any bias in the publication, it's going to be a problem. If only studies that achieve some positive result are published, and the ones that don't are not published, and you combine them together, you'll get a highly significant result, which is completely bogus because you don't have a fair sample of all the studies that were carried out. And this may seem unlikely or not important, but in fact, historically, it's been incredibly important, because some journals simply do not publish studies unless they achieve a positive result in some way above a certain level of significance. Well, there's a formula that a psychologist, I think this was like 30 or 40 years ago, developed to try to assess the potential for publication bias in terms of the number of studies that were published and estimating the approximate number of studies that were not published for whatever reason. And this has been used a lot in medical, in deciding what drugs go on have been tested and are safe to be put on the market. Well, it turns out that this, first of all, publication bias is a really big effect. And as I mentioned, there are actually journals with this editorial policy in print. That is, they don't publish a study unless it achieves a positive result. And
medical journals or journals? Do you have examples you can share?
yeah, I wrote a paper on this that has a whole bunch of references. Yeah, but the reason I'm going through all this is that I went back and looked at this formula because it seemed like it was doing something for nothing, and it turns out it's just completely wrong. The original paper, equation 1 in the paper, is just wrong. And the astonishing thing is that this result has been used for decades uncritically. People find that it almost always validates the use of meta-analysis. And so people say, oh, great, I don't have to worry, my results are good. And if anybody went back and looked at the origin of this formula with an open mind at all, they would have seen that it was completely wrong. And just trying to educate the medical profession and another aspect is that this is used in certain sort of pseudoscience things where you anyway, I won't get off onto that, but I first got into this through a sort of sleazy backdoor rather than through the medical end of things. But some statisticians understand the problems completely, but it hasn't been communicated too well to the medical profession. So when you hear about clinical studies and combining them in meta-analysis, take it with a grain of salt. Here's another statistical. Here's some references, and this is my paper. This is the original paper by Rosenthal in 1979. This is called the file drawer problem. If you Google that, you'll find a lot of stuff, because the notion is the unpublished papers are filed away in the experimenter's drawer and never get published. Yes?
You should be able to validate your prediction by, if those results were used by venture capitalists to fund drug companies and ideas, those products should not work, right? That's what you're basically saying, is that there was a wrong correlation there.
Okay, the comment was, let me try to paraphrase, that sort of a ground truth for this could come from venture capital companies who need things to work, and they don't want to be fooled by manipulating data like this. Is that basically your point? You would think so. It's a complicated thing. In fact, one of the major threads I found was that there's a lot of the research on the effects of secondhand tobacco smoke where there were small studies funded by tobacco companies and then they were combined together. And for some reason, that was one of the major threads in the medical area. And the meta-analysis studies were just completely bogus because they ignored this publication bias effect. Okay, here's another, this is an anecdote, and I maybe apologize for bringing this in. I don't normally talk about anecdotes like this, but I was so stunned to have this happen. I was driving into work one morning before the election, and there was one of those talk shows, and the president of a major political polling organization, who I don't want to name, I could, but since I haven't been able to get him to respond to my questions about this, I'll just call him Dr. Z. And a caller said, I don't respond to polling calls. I hang up if a polling agency calls me because it's an intrusion of my privacy. And this led to a little discussion of whether this could be a bias, something like the cell phone bias and things like that. And then this eminent president, Dr. Z, said, these are almost his exact words, "I don't worry about biases like that. We just get a larger sample." And I was so stunned by I mean, if you know any statistics at all, you realize that's insane. Getting a bigger sample, just if there's a bias, makes it worse because you think the variance looks smaller because you have a bigger sample, so you're more confident of your result. So I even called in. I got to my office and called in to try to verify, did he really mean that? And either he didn't understand or he was just stonewalling or something, because he just said, oh, my polls are reliable. So again, when you hear results of polls, keep this in mind. Yes?
Just to let you know, Jeff, State of California, when it adopted its lottery system, consulted a professor of business school up at the University of British Columbia, and he goes by the name Dr. Z, so you might want to
Okay.
Dr. Y in this particular
Well, okay. Thanks for the comment was that there is another presumably Dr. Z. I was sort of trying to be cute. The real person's name begins with the letter Z, and I think many of you may know who it is. But
I'll just let you know that
yeah.
there's this respectable
Yes.
scientist out there who does
Yeah.
go by Dr. Z.
Right. Yeah. Was there another question?
Your comment about what he says can actually be interpreted differently, right? Because I don't worry about such biases, meaning if it's a political poll, either side may equally drop the phone, right? And secondly, he's maybe arguing that in order to get what he believes to be his correct error, he's just simply saying, well, if we have 1 in X number of people who drop the phone, we need to have a larger sample in order to get to what we believe to be our correct error. So what he's saying when he's got a larger sample is not that the biases that he's trying to deliberately overcome, he's just simply treating the biases, or rather what you would call biases, he's simply saying those hang-up phone calls are nothing more than data loss, and he's trying to make the sample size up to allow for lost data, essentially.
Okay, the comment was, there were two parts to it. One was that maybe what he was saying was that this hang-up occurs equally on both sides. Well, that's possible, and that's why I call it a potential bias. And in fact, you'd have to find some connection whether maybe liberals are less likely to regard, either more or less likely to regard being called at dinner time as an intrusion of privacy or something like that. That's quite right, but in fact, the discussion centered around possible real biases. The second part of the comment, I think misses the point because just increasing the sample size makes the statistical errors get small, but for example, if this bias is a 1% effect and you get a bigger sample, it's still a 1% effect. So that's the key point. You don't get the bias error doesn't decrease with an increasing sample size. In fact, it looks more significant because you judge the statistical errors and you say, my result is above statistics, but that's misleading because
The advantage they have, and I don't know if that's obvious or not, when we were talking about this,
Yep.
so that's not relevant, but I mean, one of the things they do have, unlike the medical stuff that you were talking about, well, not medical one, I'd say the epidemiological studies that you mentioned, is that they do at some point actually have direct confirmation as to how good their polling is, right? So if they take a poll right in front of an election, and indeed their results are indeed exactly what the election results say, then they have confirmation.
Okay.
So they do get that at least on every some occasions.
Okay.
Even most of the polling data is useless throughout the year.
Okay.
Right up to a point where they can measure the election or whatever. It's really
Okay. Okay. The comment was that, in fact, there is some check of polls based on the reality of elections, but the point is, before the election, there were a whole bunch of polls going all over the place, and as you know, who sponsors the poll is a big factor, and so on. But okay, well, let me get back to this is probably the subject the subject that I was asked to, or the reason I was asked was probably has something to do with planetary detection. There's an algorithm that I developed a number of years ago that's been used by Jeff Marcy and others. It's a simple algorithm to take time series data of radial velocities or something else where the sampling of the observation times is not evenly spaced, and getting a power spectrum estimate, that is a way of detecting periodic components to a signal. And I could spend a whole talk about that, but I'm just going to mention that here's another here's a way in which the algorithms I really want to talk about, namely the Bayesian block thing, can be applied to planetary detection. This is some data from a transit. You probably all know that the Kepler satellite is up, and it's hopefully measuring transits of planets in front of stars, something like this. This is some ground-based data for 3 different transits at different times for, actually I don't even remember which star this is. I'm sure there's people in the audience who know. But just for fun, I thought about applying the Bayesian blocks algorithm to this data to see what you can make out of. And here's a different plot showing the error bars in more detail. And the red curve is this I call it the optimal piecewise representation of the data. It's the best representation of the raw data where each segment is represented as constant intensity for the star. And I'm not going to, there's no great scientific conclusions, but I think the fact that these noisy data give roughly similar light curves for the transit is useful. And if you wanted to calculate something like the time of decay or the rise time as it comes out of the transit, you could do that using this block representation that kind of optimally gets rid of the noise and represents only the true signal. In other words, the claim is that any variation within this interval is just random statistics and not true variation. So we can think of it as a way of getting rid of noise. But the periodogram, which is what I mentioned earlier, a way of generating a so-called power spectrum, which tells you when there's a periodic component, and of course the whole approach to planetary detection that Jeff Marcy and others have used by measuring radial velocities looks for a periodic signal in the data because of the perturbation of the planet on the motion of the star. And these next few slides are from Jeff Marcy and his co-workers. They're not mine, and this is just I won't even go into this. Just the periodogram that kind of was initially used is called the Loam-Scargle periodogram because it came out of 2 papers, one that Loam wrote and one that I wrote. Just as a footnote, I mean, modesty prevents me from talking about this too much, but this paper is the one that is most referenced of all the papers I've ever written. And I almost didn't publish it because I thought when I got these ideas, I thought this was so sort of mathematical and arcane that no one would really be interested in it. So I almost didn't publish it, but It's one that has been used in variable star work and planetary detection and all kinds of things. And other papers that I thought were really great and published with relish has been totally ignored. So I guess the lesson is, at least for me, I'm not very self-aware or something like that. But I've been intrigued by the fact that the original idea of the periodogram, the Loam-Scargle periodogram, has been extended in a bunch of different ways. One is, and again, don't worry about the details, one is called the floating mean, where instead of assuming that over the time series there's a constant component that's constant over the whole time series, what you do is to allow that mean value to float, and it's sort of like a detrending process where you allow for a smooth variation of the signal that you kind of take away and don't include in the periodic part of the signal. And there's even an extension of that where you allow not just a floating mean, but a floating parabolic fit to the background. And best of all is where you take into account in constructing the periodogram that the signal isn't just a random sine wave. In fact, it's a projection of a Kepler ellipse onto the sky, and you know what shape that is given certain parameters of the ellipse. So in a way, this is an extension of the periodogram that allows not just, that doesn't look for just pure sine waves, but looks for signals that follow the known physics of the orbits of the two-body problem, or in other cases, the multiple-body problem. In fact, this has been applied to cases where there are more than one planet around a given star, and it allows you to separate the signal from the planets from each other, and that's a very nice thing. And at some point, we can even understand the gravitational interaction between planets using extensions of this kind of technique. And here's another extension where you do the periodogram in kind of a two-dimensional way. You allow there to be two frequencies. Let's say there are two planets around the star, and you do a two-dimensional power as a function of one frequency and another frequency. And you see there's some artifacts that are like, they're called aliasing or ringing of the algorithm given a signal. But the highest points, if you looked at this as a three-dimensional plot, the highest points are at these two points where the two planets at two different frequencies stand out. And these other smaller peaks are understood as aliases of the main peaks. So it's been interesting to watch the development of this idea that I and others had quite a while ago, and applied to a bunch of topics, in particular planetary detection. Okay, here's the kind of the subject. Let's see how we're doing for time. Yeah, okay. This is a new topic, so any questions about what I've talked about before? Okay, this is,
Jeff,
sure.
published that first paper?
Oh, I think it was 1980 or something like that. It's been a while, yeah. Okay, at the beginning I mentioned that that there's a smallest scale, the Planck scale, at which for space and time, and in addition to that, there's a notion that on the smallest scale, on the Planck scale, space-time may very well be discrete and not continuous. What does that mean? That sounds maybe hard to understand and or crazy. We know that space is continuous. If you move something, you can move it by any amount you want. There's no clicking of positions according to some small quantum of space. But that intuition that space is continuous is really just based on that intuition from macroscopic scales that we can observe. The Planck scale is so much smaller, and even if you didn't know about the Planck scale, this scale of electrons and quarks and the elementary particles is so small compared to our physical intuition that who knows what goes on at that scale. So there are two quotes I could give where both Bernhard Riemann and Einstein were aware of the possibility that space could be discrete and not continuous. And that would mean that if you look somehow with a microscope at the Planck scale, space is not continuous, and things can only occupy like a grid of positions in space. Einstein was aware of that possibility, and general relativity, of course, says just the opposite, that space is continuous, but it's certainly possible. Well, I mean, that's such a small scale, so what? The point is that if space-time is really discrete, then light traveling from distant objects is kind of like undergoing a random walk. It doesn't go in a straight path, a continuous path. It goes, it sort of stops along the way at various points that may be randomly distributed on a very small scale. So if you work out sort of the mathematical theory of that, which I'll just briefly touch on, it's possible that the propagation of photons would be affected by this discreteness. And in fact, the speed of light might be slightly different at two different energies. A high energy photon might travel at a different speed than a low energy photon. And if that were so, it could possibly be detected. A very small difference in the speed of light accumulated over astronomical times could build up to possibly a significant time. And that's the point of using the Fermi used to be called glass, of using this gamma ray telescope. Gamma ray bursts that I gave an example of, the light curve, have very sharp features sometimes. And those sharp features also correspond to a large energy range and a large travel time, so this tiny effect could have built up. So potentially, by measuring light curves of gamma ray bursts, one might uncover an effect. And it's called quantum gravity. And this is just a kind of an introductory thing about unifying quantum mechanics and general relativity. And obviously, I'm not even competent to go into a lot of details at all. But the fundamental problem that everybody talks about and people write books about and so on is really pretty fundamental. General relativity is on the large scale. It's a deterministic theory, and there's sort of a technical thing that it's background independent. That is, it doesn't assume that there's an absolute space like Newton did. Quantum mechanics is on the very small scale. It's a probabilistic theory as opposed to a deterministic theory, and it assumes an absolute background in some sense that I can't go into details about. So there's been a lot of stuff written about this. And in fact, here's just a small sample of approaches to quantum gravity theory. You hear about string theory, and some physicists, especially at Stanford, think that's the only quantum gravity theory, but there are a whole bunch of them, and this is just a few of them. And I'm interested in this particular one because it's sort of, this is the one that most dramatically postulates the discreteness of space-time. It literally says that space-time is a set of points that have only causal relationships. And for example, the concept of the distance between points is not even defined. And it turns out that not only the effect I was talking about earlier of measuring light travel time effects in gamma ray bursts is called dispersion in gamma rays, but now there's a whole bunch of other possible astrophysical tests of quantum gravity effects, which are sometimes called Lorentz invariance violation, because that is what's really going on in the theoretical approach, is that is the structure of physics that the Lorentz transforms embody is being violated in some sense in these theories. And let me skip through this. This is just some mathematics that shows how you can get a rough notion of the scale of the time delays that might show up in a gamma ray burst. But the reason I show this is I'm pretty critical about taking this at face value, because what this does is it's not a real prediction. It just says, let's take the ordinary relationships from classical physics and assume that we can expand them in a Taylor series. And further, let's assume that the scale of the coefficients in that Taylor series are set by the Planck scale of energy. And so you can plug numbers into that and get predictions. If you do that for gamma rays at the other end of the universe and the Fermi timing accuracy and so on, you get that this could be measured, that this delay time over the energy range of Fermi could be as big as 1/10 of a second, and that would be really easy to measure in terms of the timing accuracy. But this is not a prediction, even though it seems like it, and people tend to think of it as a prediction. It's more to say that the theory allows this effect rather than predicts this effect. So let me go pretty quickly. This is to show you that there is a real fundamental problem in that we don't know that the signals generated by gamma ray bursts are simultaneous at different energies. In fact, we know that's not the case, and that this is just to show a cartoon of graphs of the light curves of gamma ray bursts, and there are known delays in the emission mechanism, so that would be confused with the assumed quantum gravity delays. And that's a real problem, and there are various ways of trying to deal with that, but it's really the fundamental limit is not how accurately you can time photons arriving at the gamma ray telescope, but this intrinsic delay that you have to account for. So I'll skip the details. There's an algorithm that I think is kind of neat because it allows you to measure the delay without doing any bending in time. You essentially adjust individual photons and maximize how good that adjustment is. So and here's a curve showing just with simulated data that you get a very nice determination of the delay, in this case 0. You know the delay is 0. And we're trying to use this on Fermi data right now. And it works great, but it's still, there's this ambiguity due to intrinsic delays is confounding any discovery of a real effect. So and here's an example of, this is the shortest known gamma ray burst from previous satellite, the Compton Gamma Ray Observatory. And the scale here is in microseconds. And this is a very sharp burst where the scale of the rise time is a few hundred microseconds. But even with this burst, you can't detect any real delay. Well, let me skip this. This has to do with some other people's work on trying to deal with the intrinsic effect by studying gamma ray bursts at different redshifts. This parameter means smaller redshift here and bigger redshift here. So any intrinsic effect might give you a delay, but if there's any effect that accumulates with distance or redshift, that's presumably a propagation effect or a quantum gravity effect. And these authors put a straight line through their data, but in the paper admit that there's really no detection. That's the errors are too big to detect anything. So and again, there's some similar limits on the speed of light from other astrophysical experiments, so to speak. But gamma ray bursts are now the best limit. This is looking at this is saying the change of the speed of light relative to the speed of light itself is less than or equal to 10 to the minus 20. So it's a very strong limit on the possible change of the. And for those of you who are radio people, you may worry about the dispersion due to the ionized gas in the medium between us and these gamma ray bursts. And I worried about that a bit and thought, well, maybe people have been ignoring it, but I found a paper that calculates it, and it's incredibly tiny because of if you put in the parameters for the mean electron density in between galaxies and so on, you get a very tiny effect at gamma rays, as I see Frank nodding. So let me skip these. These are other limits on related quantities from astrophysical experiments. And let me just conclude with this slide, which kind of summarizes a bit of what I've said. This is applying the the notions of Voronoi tessellation to the smallest scale. There's actually a physical theory by T.D. Lee called, I forget what he calls it. It's lattice cell dynamics or something like that, where the postulate is that on the smallest scale, on the Planck scale, space-time is not only discrete, but it's distributed according to Voronoi cells, that is, random points with cells where each cell represents a kind of a blob or a fuzzy blob of matter or something. And again, no details, but it's a physical theory that invokes Voronoi tessellation at this Planck scale. I showed you examples of using Voronoi tessellation at the scale of the focal plane of the Fermi telescope. Here's an example that I would have loved to have talked the whole time about, namely taking redshift surveys. This is the Sloan Digital Sky Survey, which measures hundreds of thousands of galaxy redshifts, and so we have a really nice 3D point distribution for galaxies. And this is a Bayesian block representation based on Voronoi cells of that data. And the result is fairly well known that the distribution of galaxies is not as simple as people thought in the old days, so to speak. Their clusters, these big fat round clusters, are not necessarily typical, that there are sheets of galaxies and filaments, and it's more like a honeycomb structure. And in fact, there's a number of astronomers who think that the distribution of galaxies on this largest scale that we know is none other than Voronoi cells, and that the so-called voids between these sheets and filaments and clusters and so on are the insides of Voronoi cells, and the sheets are the faces of the Voronoi polyhedra. The filaments are the edges of these cells, and the clusters are the nodes of the cells, so that there's a really nice picture of the distribution of the largest scale structure that's based on Voronoi tessellation. There's a physical theory at the very smallest scale, so maybe all of the universe is nothing but a Voronoi tessellation. Thank you.
Thanks very much, Jeff. Do you have time for questions?
So Jeff, it looks like what you need is a gamma ray burst happening behind a grav lens, so you can do interferometry, right? I mean, basic idea of sorting out everything, it'd be neat to be able to compare one narrow wavelength with itself and see if there's any delay due to increased path length. That seems like the only way you could do it, right?
Well, unfortunately, that would be a small difference in path length. The beauty of this idea is that you accumulate this effect over the entire billions of years in time or Hubble distances in space. What you're saying may be more controlled, but it's a smaller effect in principle, so I'm not sure that. And it would be really tough to arrange for that to be detected, I think. So. Frank?
And a historical note. I don't know how long ago it was, but at least 40 years ago, Peter Van de Kamp at Sproul Observatory believed that he had detected a Saturn-sized planet orbiting the second nearest star, Barnard's star.
Right.
And he took data for years and years of the perturbations and proper motion of that star. And then what he did was to eyeball the deviations from straight line motion and say, I think I see a periodicity.
Mm-hmm.
And then he tried to fit a sine wave with that periodicity using least squares.
Yes.
And when he did that, he got a positive result. He got
Yes.
a sine wave that fit with an error bar whose significance you can't really tell very well from the observations. And for years he was claiming that he detected the first extrasolar planetary system. Now he was a real nice guy, and I used to talk to him a lot. So one day I said, I want to take your data and spectrum and Fourier analyze it to see if there's a period in it using an unbiased approach, which is Fourier analysis. So he gave me all the data, and I did the Fourier spectrum. and there was no significant period in it. Completely unbiased result.
Yes.
There were a couple of peaks that are 1 sigma or something,
Yeah.
and in the long run, it turned out that his least squares fits were misleading.
Yeah.
Because with any set of data, if you fit a sine wave whose wavelength is about equal to the length of the data stream, you get a positive result in a least squares fit. And that
Yeah.
was what was going on.
Yeah. I can actually add a little footnote to that. There was a technique called the maximum entropy spectral analysis method that was popular back, I guess, after the time you're talking about. And some geophysicists, one who's a good friend of mine, Tad Ulrich, actually wrote a paper announcing the discovery of 4 planets around Barnard's star based on the same data you're talking about, using this fancy method, which essentially was overfitting data incredibly. And that's just a little footnote. People can go off on deep ends with data analysis. It's, as you pointed out. Yeah.
I was interested to know when you correlate gamma ray bursts with other pieces of the electromagnetic spectrum, say ultraviolet or infrared or visual, do you see any delays in events there?
Well, okay, that's a good question. Unfortunately, the sharp event, what's called the prompt emission from these objects, is confined totally to the gamma ray region of the spectrum. We now know that that other radiation leaks out. That's called afterglow, and in fact, that's one of the biggest advances in gamma ray burst astronomy was finding those and being able to identify the host galaxy where the gamma ray burst occurs based on those afterglows. But those are very, very smooth. They're not sharp, so you can't measure a delay. In fact, almost certainly the emission is coming not from this explosive event that generates the gamma rays, but the interaction of the blast wave coming out of that event with the medium around it. So it's a good idea, but there's no way to get a sharp feature. The key thing is that some of the bursts have these very sharp kind of knife edge features that allow accurate timing.
Great. Well, Jeff will be around for a few minutes additionally, but let's wrap up for the hour and thank him one more time for his nice talk.
Thank you.